Hey guys, what's up? It's me, Martin, the amazing talking panda, and also the lead designer, back with part 2 of optimization. In the previous video, we went over what the FPS rate in video games is, because without first understanding what the result we're after is, we wouldn't be able to achieve it. Some of you have been wondering why we're doing videos like this, and the reason is we found out some members of the community think that video game design is just buying a bunch of content on the marketplace, slapping it together, and well, that's all there is to it. But I get it, as consumers, not many companies take us behind the scenes to see what's really going on. So we're gonna take you there a little bit as we work, so you can get an idea of everything that goes into making a video game become a reality. Anyway, now that we know what FPS is, let's take a look at what we can do about it. So a video game basically consists of two parts: the visual part, which is everything we see on screen, and the logical part, which is behind the scenes, the game mechanics, collisions, AI, and so on. The visual part is handled both by the CPU and by the GPU. The logical part is handled only by the CPU. This means that our game's performance can be slowed down either by both the CPU and GPU or only by one of those components. To see which component is holding us back, we can type stat unit into the engine's command prompt, and this comes up. Game means the game logic. Remember, that's only handled by the CPU. Draw is the visual part that the CPU is responsible for. We'll talk about that a little bit later. GPU is only the video card. So remember, to get 60 FPS, each frame should take roughly 17 milliseconds to render. And that's about what I'm getting on my PC right now. Now keep in mind that I'm recording the screen, so I'm getting slightly less FPS than I would be if I wasn't recording my screen. And we can see that the GPU is taking the majority of time to render each frame. Therefore, our visual part needs to be optimized. If we manage to lower the time that the GPU takes to render each frame, we can either make the game run better on PCs with older video cards, or we can free up more resources for the logical part of the game. So let's go and have a look at how we can optimize the visual part of the game. By the way, for anyone wondering, these are the PC specs that I'm currently on. We have an Intel i9, 32GB of RAM, and a GTX 1060 video card with 6GB of video memory. And according to the Steam Hardware and Software Survey, as of March 2021, these are the average Steam users' PC specs. 16GB of RAM, which is about half of what I have, a 4-core CPU, which is considerably less than I have, and a GTX 1060 video card, which is exactly the same as I have, but with slightly more video memory. So as you can see, even though I'm getting quite good results, we still have some work to do on optimization just to make sure that the game runs well on other people's PCs too. And if memory serves me correctly, there's a gentleman from Holland in our Discord who said he has some spare PC parts that he could send us for testing, so I'm gonna have to get back to him on that. And meanwhile, why don't you guys join our Discord? You'll find the link in the description box below. The visual part of the game can be divided into three basic parts: meshes, shaders, and passes. We're going to start with meshes. Pretty much everything we see on screen is a mesh. The cars are meshes, the buildings, the roads, the trees are all meshes. And meshes are just basically giant big graphs onto which points are plotted just like this. Just like we did in school, or if you've ever done one of those magazines where you have to connect the dots with the numbers and then you get a picture. That's exactly what this is. There we go. Oh, that's a pretty ugly looking box, but I think you get the idea. They're connected like that with edges, and then the space in between the edges can be filled in with faces like this, onto which textures are applied, and we can create any 3D model we want like this. The more points that your model has, the more resources your video card needs to render it. So the first most obvious thing we've been doing is reducing the number of vertices or points on all our models by creating LODs. You've seen how that's done already in previous videos, but just to recap, you make a few versions of each model, each containing less points than the previous one. If we look at this train carriage over here, LOD 0 has 25,000 points. If we switch to LOD 1, it's only got 15,000. Switch to LOD 2, it's got 7,000, and so on. Then the engine will automatically switch these models as the camera moves away from them. So I'll show you guys how this kind of works in the engine. If we switch our viewing mode to level of detail coloration and mesh LODs, you'll see that the train carriage in front of me has turned white, which means that we're seeing the original mesh, and as we start moving away from it, it'll start turning red, which means it switched to the first LOD, then it'll turn green, which means it switched to the second LOD, and then at some point it'll turn blue, which is the third LOD, and so on and so forth. Now there are currently two ways of going about making LODs in Unreal Engine. You can either make them by hand in your modeling application, or you can use a feature in Unreal Engine to generate them automatically. So let's have a look at how that feature works. I've created a copy of our train carriage here, and I'm gonna scroll down here and say that we want this particular model to have two LODs. Apply those changes, switch to LOD 1. And as you can see, there's already all kinds of problems with the materials in wrong places when trying to generate LODs automatically. But let's proceed anyway. Let's say that we want 10% of the initial vertex count and apply the changes. And as you can see, the results are decent, but well, they're decent in some places, but in some places there's all kinds of points sticking out. And for example, this little part here could have been completely removed. And the results are just not as good, clean, and well optimized as if a human was doing it by hand. So on large models like this, you really have to do them by hand. On small models, you can get away with using the automatic feature. But for the most part, we had to do LODs by hand, which was the most time-consuming part of optimization. To further reduce points on the screen, we can set up max draw distances. These are distances at which objects just disappear off the screen. There is no sense in using up resources rendering a small object that can't even be seen anymore because it's too far away. So let's have a look at how that works. I'm going to set up a max draw distance on this mailbox on the right here. So let's set that to like 300 units, which should be, whoops, that's too little, 3,000 units. And there's a bug, you have to reset that and then input that again. There we go. Now when I move away from this mailbox, the one on the right should disappear. And there it goes. Now this does present a problem because we have sniper rifles in game. So even though an object is too small to be seen right now, when you're looking through the scope and the field of view of the screen changes to something like 20, well, suddenly you should be able to see the mailbox, which is now hidden. So we can't really set max draw distances too low in our particular game. This ties into draw calls. Remember when I said that the CPU and GPU are also both responsible for rendering the visual part of the game? Well, for every mesh on the screen, the CPU has to send the GPU a draw call, which is basically like, hey GPU, I need you to draw a train carriage at the following coordinates and apply these textures to it. And that's all fine and dandy when there's only a few draw calls, but when there's thousands of them, your PC simply just can't keep up. So the less meshes that are visible, the less draw calls there are, and max draw distances, or culling, play a big part in that. That's why sometimes you get games with very detailed scenes, but the view distance is only like 400 meters. Let me go ahead and place a train carriage into the scene like so, and type stat rhi into the command prompt, and I'll make that bigger for you guys. As you can see, we're at 190 draw calls. Now, if I go ahead and copy paste the train carriage like so, watch what happens to the number of draw calls. As you can see, as I'm doing that, the number of draw calls is slowly creeping up. And if I do that enough times, eventually we'll reach thousands of draw calls and our FPS will slowly begin to go down. Now let me go ahead and delete all these train carriages and I'll show you what else we can do. What if I place the same train carriage using Foliage Painter? Check this out, 134 draw calls on empty scene, and I've just painted maybe 100 of the same train carriages into the scene, and we're at 172 draw calls and our FPS rate hasn't even reduced. The FPS wasn't reduced that much because we removed the draw call constraint and are now only limited by the number of vertices that the GPU has to render. That's because Foliage Painter treats all the meshes as one mesh, so the CPU only had to send a few draw calls and the rest of the information were just coordinates where the mesh should be duplicated. Way less work than placing the carriages individually as we did the first time. Instant static meshes are great for things like pavements, roads, fences, and nature. Speaking of textures, that's another thing that needs to be kept in mind. Although 4K textures would look great everywhere, check this out. I've got a 2K by 2K texture here and the file size is 2700 kilobytes, so almost 3 megabytes. And check out what happens if I change the LOD bias to 2, which will change the texture's resolution to just 512 by 512 pixels, which is 4 times less than 2K. The file size is now just 171 kilobytes, which is 16 times less than a 2K texture. Let me change that back quickly so we don't accidentally ship the game like that. So the larger the textures are, the more memory you need on your video card to store them, and you also have to keep in mind that the textures have to be processed by the video card and also sent from your hard drive to the video card. Sending a bunch of 4K textures will take up your bandwidth pretty quickly. So it's important to decide which meshes actually need high resolution textures and where smaller resolution textures would do perfectly fine. So we've done all the LODs, we've done everything we talked about. Why is my video card still the bottleneck? Well, this moves us onto shaders. You can think of shaders as skins that you put on top of the meshes to make them have colors and details. Shaders range from very basic ones that just add colors or details such as bumps to very complex ones that add various fire and water effects and so on. So what we can do now is we can go to view modes, click on optimization view modes and shader complexity, which will show us how complex our shaders are on every mesh. And as you can see, our buildings are green, which means that the shaders on our buildings are very well optimized, but some of our clouds are red, the landscape is red, and some of our nature is even red to white, which is bad to extremely bad. So what we need to do now is go back and optimize some of these red shaders, which will greatly improve performance not only on my machine, but even on slower machines. But that's a whole different video for a whole different time. I'm not going to go into that right now, but do leave a comment in the comments below if you're interested in seeing how that's done. Now, if you made it this far into the video, the last thing we'll look at are rendering passes. Each of the 60 frames that appear before our eyes every second consists of a few frames themselves. These are called rendering passes. You see, a frame isn't just rendered in one go. First, the base pass is rendered, which is where all the meshes and basic materials are. This is the most important and time-consuming pass. Then on top of that, you have a bunch of other passes which add ambient shadows, bumps, reflections, lighting, opacity, shadows, post-processing, and so on. So if I type in stat GPU into the engine command prompt, we can see how much each pass is costing us. So for example, here we can see that post-processing is costing us about 0.32 milliseconds. We can see that lights are costing us about 0.29 milliseconds, and I can go ahead and click on my light here, that's my light source, and I can uncheck visible to turn off the light, and now you see lights are costing us nothing because I've turned them off. Another thing I can do is I can type shadow into here and notice the FPS. We're at about 64 FPS now. And notice the shadows here. Hold on, let me hide those statistics. So notice the shadows, they're kind of blurry, and we're at about 80 FPS when we're looking into the ground right now. If I change the number of cascades in the shadows to 1, for example, I'll make the shadows very blurry. Well, now we're at 120 FPS. And almost 90 FPS just looking around the map. And now if I increase the quality of the shadows to 2 cascades, we can see that the quality of the shadows is getting better, but our FPS is slowly decreasing as I increase the number of cascades. I'm not going to go through all the passes, but hopefully that gives you a rough idea of what they are and how they also affect performance. So as you can see, everything we do is basically a balancing act and a trade-off. You know, we've seen a lot of content on the marketplace which looks good, but the texture compression settings are wrong, there's a zillion draw calls, and sure, they get 60 FPS in their demo, but there's one house on the entire map, and the whole thing is unusable for anything else. So if you guys take away anything from this video, remember this: design isn't just about the way something looks, but about how it works. Anyway, give us a thumbs up, subscribe, support us on Patreon at patreon.com/TavianaTheOrigins, and I'm off to finish optimizing the game. Smell you guys later.